Swayam Prabha. Digital India. Educated India.
We are going to start a new subject today, that is on massive transformation. Massive transformation is a relatively newer terms to you because it is a solid state transformation, but it is not widely taught in the different colleges. So, let us first explain what is a massive transformations. To do that, I will use phase diagram initially, and then I will go into the microstructures. As you know, the transformation of a single solution phase by nucleation and thermally activated growth to a product of same composition is known as a massive transformation. So, this is distinctly different from martensite. In martensite also, the gamma transform to martensite in steels without changing any compositions, but transformation does not happen by thermally activated growth. So, distinct difference between a massive and a martensite is that here a solution phase, single solution phase transform by nucleation and thermally activated growth to a new solution phase without change of any composition. And this happens when the sample is quenched again. So, that is the main difference of that, of the definition of the massive transformation. So, let us explain it in the terms of phase diagram. Mostly copper based phase diagrams show this kind of transformations, but there are other phase diagram also which I will report you later. So, let us first take this slide where it is a copper gallium phase diagram and taken from Professor Masalski's book on binary Euler phase diagram. We are showing only the copper rich part of the phase diagram. So, as you see here, suppose I have a high temperature beta phase in the phase diagram and which has a BCC structure, and alpha is a solution again which can actually retain large quantities of gallium. As you see at room temperature, it can retain approximately about 18% of gallium. So, now if I take an alloy composition given by 1, Roman 1, and if I slowly cool this alloy composition, what will happen? This alloy is at high temperatures, as about 900 degrees Celsius temperature, it has a single phase BCC or beta structure rather. So, as you cool it down, it will go through single phase to a two phase alpha plus beta, then it will go to again to a single phase alpha. So, what will happen once the temperature is reduced from 900 to about 800 or 830 degrees Celsius temperature, this alloy will come into two phase regime. So, in which alpha and beta will be coexisting and their compositions will be given by the tie lines. If I draw, you can clearly see the tie lines, alpha composition will be given by this point and beta will be given by this point on the right side. So, but as you know, once it is passing through this two phase region, this kind of a two phase microstructure will form, consisting of mostly Widmanstatin alpha in the beta grains. Now, what will happen as you cool it down below this temperature, something like 800 say 700 degrees Celsius temperature, then it has to transform into fully alpha phase. So, whatever beta will be there at temperature above 700 will be transformed to alpha, because below this temperature alpha, single phase alpha should be present in the microstructure. But as it happens, there is a partitioning of solutes between beta and alpha at temperature between 700 and 830 degrees Celsius temperature. So, this is what will happen to a alloy 1 when you slowly cool, and it is easily explainable from the phase diagram. Now, something else can also happen, actually different kinds of situations happen. If we take this alloy composition 1 and rapidly cool or quench rather from say 900 to about room temperature, directly, not so rapidly, but at least rapidly enough, this alloy will not go through this two phase region. It will directly transform into something known as alpha M without change of any composition. So, beta will transform to alpha M without change of any composition, and this transformation is known as a massive. Reason this is known as a massive is because the alpha M transform massive comes or forms rather as a massive blobs at the gain boundaries of the beta, and importantly the nucleation of these alpha M happens on the incoherent gain boundaries of beta. That means alpha M does not have any preferential orientation with the beta phase. This is typically happens in a copper gallium alloy composition given by this one. Now, let us take another alloy which is given by 2 here. This alloy is again single phase beta structure at high temperature. At about 800 degrees Celsius temperature, this is a single phase beta structure. Now, if we cool down slowly, what will happen? Equilibrium situation will prevail because phase diagram tells you equilibrium transformations. As you cool it down slowly, there is, you see, beyond this point, this should transform into two phase mixture of gamma plus beta. That means gamma will start forming out of beta, and slowly this at this below this line, this they will actually should transform to something else. So, basically it should have a mixture of gamma plus beta at this temperature range. Now, it so happens that, very interestingly, it so happens that if you quench this alloy 2, this will not undergo this two phase separation of gamma plus beta, rather beta will transform to what is known as epsilon M. Beta will transform to epsilon M, massive epsilon phase, because if we extend this line metastably, this is metastable extension of these gamma line or gamma existence line, this is what lead to epsilon, this is not gamma, we should extend, this is epsilon actually, this is epsilon line, because below this line epsilon phase starts forming, okay, here you can clearly see that. So, that is why epsilon will come out, and this epsilon is not a stable phase here, it is a metastable phase. As you see here in this region, epsilon plus gamma 1 should exist, but because epsilon M directly forms from beta in this composition range, so it is called a metastable epsilon. On the other hand, alpha M, which is forming directly from beta for number 1 alloy, is an stable phase, it is not a metastable phase, because it should be having alpha phase in the phase field given by this phase diagram. But here it should have epsilon plus gamma or gamma 1, and basically that does not happen. When you quench the alloy 2, it forms directly massive epsilon or epsilon M. So, as you clearly see that these transformations are very common in these alloys, and these have been observed. Basically the reason for such a kind of transformations were observed, again serendipity, some scientists wanted to quench these alloys from high temperature, but did not quench sufficiently enough to form martensite. They quenched it little bit slower, that is why this leads to formation of a new kind of a morphology of these phases, and the transformation happens in such a way there is no compositional partitioning. So, basically it clearly tells you that as there is no compositional partitioning, so transformation is completely thermally driven. That means thermally activated transport of atoms across these alpha beta interfaces do happen, and that leads to formation of this phase. So, this is one example which is very interesting. Now, another example of these is this copper zinc, that is brass, and this is the equilibrium phase diagram of copper zinc, again taken from Professor Masalski's book. As you clearly see here, there is a large alpha. Alpha is FCC phase in copper zinc, remember, and beta is a BCC phase in copper zinc. The copper zinc and copper gallium phase diagrams have a lot of similarities, but not at low temperature or higher temperatures. As you see, alpha, beta, gamma, all the phases are present. Now, as you see, if I if I ask you to focus on these dotted line which tells you alloy composition given copper 38.3 weight percent atom percent zinc rather. So, this alloy at about 830 degree Celsius temperature, 840 rather, is basically is a single phase beta. Now, as you cool it slowly, again this will transform into alpha plus beta, alpha plus beta, alpha plus beta, alpha plus beta, and then here it will transform to alpha. That is the equilibrium transformation will follow like this way. Now, it seems that if we quench this alloy again from high temperature, then it does not form alpha plus beta, it does not undergo alpha plus beta partitioning, rather it transforms directly to a massive alpha, or what is known as alpha M. Similarly, like copper gallium. So, these are actually observed in many alloy systems, like I can tell you names: copper zinc, copper aluminum, silver cadmium, silver zinc, silver aluminum, even steels, iron carbon, iron nickel, iron chromium, iron cobalt systems. So, this is a general feature of the many of these systems. So, how now that we understood this is how the transformation happens, before we talk about the other things, let us see how the microstructure actually looks like, because microstructure is very interesting. This is how the massive transformation products looks like. This is taken from copper 38.7 atom percent, it should be atom percent not weight, atom percent zinc quench from 850 degree Celsius temperature. The same alloy which just now I shown you, this alloy 38% 3 atom percent zinc alloy is quenched from 850 to room temperature. So, what will happen? This was the prior beta grains, okay, this is a beta grain, okay, you see here, and these are the gain boundaries of beta. Now, massive alpha has formed on the gain boundaries, this is alpha M on the gain boundaries and grown. Very simple, that the nucleation of massive alpha will be heterogeneous type. Why? Because they are growing nucleating incoherently on the gain boundaries of beta. So, whenever there is incoherent nature of nucleation, it must be heterogeneous, and this happens along the gain boundaries and the gain corners of the prior beta grains. So, and then subsequently growth is basically thermally activated, there is no compositional partitioning required. Alpha and beta has same compositions as what we saw just now. So, as alpha and beta has same compositions, the growth of alpha M into beta is basically nothing but a transport of the atoms from beta to alpha. Remember, this is where the distinct difference to the Martensite transformation will come into picture, which we will discuss a little later. So, because its interface is incoherent between the alpha M and the beta, so only thing which requires interface can grow very easily, because there is no coherency between the interfaces of alpha M and beta. So, only thing you require is a thermal jump of the atoms from the beta to the alpha. That is what it is, because it does not require any kind of partitioning, there is no compositional difference between these two phases. So, this is very fast, very fast things happens in the microstructure. That is why alpha massively grows into the beta grains and completely transform the whole beta into alpha in a very small time scale, and compositional partitioning always require diffusion. So, this is a diffusional less transformation, by the way, but not a military type like a Martensitic transformation, where shear forces actually on the glycyl interfaces leads to the transformation, but here that does not happen. Here transformation does happen by simply thermal migration of the atoms across the interfaces. So, that is the one of the product which is taken from direct Hull, okay, HUL and Garhoots. It done long back 1956, but it is there in the book also. This is another product of massive product. This is on a copper aluminum alloy, copper 20 atom percent aluminum alloy, quench again. I am not showing the phase diagram, you can check on the literature also, from the beta field at about 1027 degree Celsius temperature into iced brine. Note the irregular alpha alpha boundaries, between alpha alpha there is irregular boundaries. This is a characteristic feature of the massive transformations. Whenever you will see a microstructure which shows this kind of irregular morphologies or irregular interfaces between these phases, then you can actually think of similarities of massive transformations. Some of the other transformation possible Benite has occurred on the gain boundaries. You can see here, this is the Benite has formed at the gain boundaries, but the main thing is that the alpha m or the massive alpha has started nucleating, and you see the interface here, it is jagged, it is basically a rough interface, it is not smooth. So, that means that incoherency was existing between the alpha m and the gain boundary of beta, which was there prior, and then they grow very rapidly because their growth requires only atomic transport. So, then not only that, between the two alpha grains the interface is also jagged, that is also characteristic features of the alpha. Okay, even not only that, you look at the interface between alpha and the beta as it grows into that. So, it was also very jagged. So, that is a clear indications of that these are actually massive alpha. The important problem or rather serious problem when trying to understand whether the compositions of the alpha m and beta are same is the measurement issue, because beta does not exist in the sample at all. So, that is very difficult to correlate that, but only way we can understand this is that if I have a single phase beta alloy, so we know the compositions of the beta, and then we can measure the composition of the grown alpha m, and then see the correspondence and tell that this is partitionless or diffusionless transformations. Okay, so that is the another characteristic features of these transformations. This is again taken from Chadwick long back in 1972. This is a very interesting microstructure of a steel. Okay, the steel with a very low carbon concentration, 0.0028% carbon. Basically, it is nothing but a pure iron. And this was the gamma phase at high temperature, and then quenched. You see, quenched from 1000 degrees Celsius temperature in ice brine. It does not form martensite because quenching was not so rapid, that is why. As you remember, as the carbon concentration decreases, the martensitic start temperature also changes because it will be much lower. The martensitic start temperature MS depends on the carbon concentration. Higher the carbon concentration, higher is the martensitic start temperature. So, very low carbon concentration steel will have very low, extremely low MS temperature. So, even cooling ice brine will not lead to massive martensitic transformations. So, these are actually massive blocks of alpha. We do not see any gain boundaries here because this is so massive, very big patches of alpha is formed. The important feature which you can see again the jagged interface or the irregular interface between the alpha grains. This is alpha, this is also alpha, that is the irregular interfaces. So, these are actually characteristic features of these as things. Now, let us just see thermodynamically what happens, then we will get back to something else. But okay, I am showing you few G versus composition diagrams at different temperatures. Okay. So, here I am showing you at different temperatures like T1, T2, T3, T4. But let me go back because these diagrams initially look like very messy, but they are very nice. Basically, we are plotting the G versus X curve for the alloy 1 here for the copper gallium system. Alloy 1 if you cool down, we can actually do this G versus X curve at suppose at this temperature, then at this temperature, then at this temperature, and then at this temperature. Okay. So, T1, T2, T3, T4 at these 4 temperatures we can do that. So, as you see that these temperatures at high temperature T1 is a single phase BCC, a single phase beta actually. At temperature T2 it has a mixture of basically beta and alpha. At T3 is just on the verge of transforming to alpha, and T4 it should be completely alpha as far as the equilibrium phase diagram is concerned. Now, let us go back, go to the next the slide which I am showing you just now. So, T1 as I said beta is a stable phase. So, you can clearly see that beta is a stable phase. Beta has a very low at lower position than alpha. But at T2 obviously there are 3 phases will be existing as the composition profile shows, alpha, beta and gamma, and 3 such parabolic inverse parabolas drawn corresponding to alpha, beta and gamma. But you know let us look at the diagrams very carefully here. See, if I have to transform beta to alpha is impossible at T1. Why? Because there is no driving force available. Very clearly that the driving force available to transform beta, because this is G, is positive. So therefore, never it will transform. Only when even at the same composition. When you cool down T2, it will have alpha plus beta mixture. You see here, this is the common tangent turn, and this is the common tangent, so alpha plus beta mixture will be stable. And that is what is shown for these alpha precipitation. The driving force available is shown between, this is basically shown by delta G alpha plus beta, and for the massive is 0, because at this temperature basically alpha plus beta has the same free energies at the same composition. You see, this is the composition line 38.7 weight percentage, and they are crossing it over. So that means the delta G for alpha m is 0. And this temperature corresponds to T0. T0 means at the temperature at which the free energies of both the phases are equal. So it is very clear, only below T2 the driving force for massive transformation will be available to the system. So this is what is clear, but at T2 it will be having these two phases alpha plus beta will coexist at the composition given by this particle line. Now as you go down the temperature at T3, what happens? As you look at T3, okay, the common tangent between alpha beta is drawn again here, and this will tell you the composition of alpha, composition of beta, right. That is what it tells from the free energy composition diagram. Now, but on the other hand, if it has to transform massively, that means there will be no compositional change from the alpha to beta. The driving force available is again given by delta G alpha m. That is quite large here, that is quite large. Even that driving force is almost same as the precipitation of alpha upon beta, because this is the driving force for the precipitation of alpha to beta. I can write down, okay, this is delta G alpha beta, that is, and the massive, they are comparable. As you go down temperature T4, massive transformation delta G alpha m becomes higher. So there is very clear evidence that the driving force for the massive transformations becomes increasingly higher as the temperature goes down. So from T3 to T4, massive transformation driving force is much larger, and that is why actually as you quench, you can bypass these precipitation of alpha on beta basically, because you are quenching rapidly, and driving force then becomes very high for the massive transformations, and beta directly transform into alpha m without change of any composition. This is very clear even from the free energy composition diagrams. So one has to really look at carefully from the phase diagram data. This will also happen in copper tin, copper zinc, which we will discuss in the next class. So it is very evident that the massive transformation is not a new thing in the literature. It would have been there, but because people have not observed it previously before 1950s, this was not discovered. So once the samples were quenched intermediately, not very rapidly to form martensites, then people could not have seen the massive products, and then we started learning what is massive, and this is a genuine important transformations which can be termed as diffusion-less transformations. But if we ask the different literature very carefully, if you look one study literature, the completely saying that it is a diffusion transformation is not correct, because there is a thermal migration of the atoms across the interface. So atoms are getting transported from the product parent phase to the product phase across these jagged or irregular interfaces, which is incoherent. Things which is not happening here, just like a martensite, as I told, is that there is no shear to transfer to change the crystal structure from BCC to BCT in case of steels or some other things, other martensite transformations. So that is the major difference. So let us stop here in the next class. I am going to discuss more about the copper zinc system, as well as whether we can bring about more analogy with the martensites.